Okay, today we're going to take a look at a new experiment in the Transference of Electric Power series. That is a comparison experiment between transference of electric power over 30 meter single wire and also over point-to-point Telluric channel that's through the ground, where the two ground systems are separated by approximately 18 meters, and we're going to be using the cylindrical coil at each end that you see here in front of on the camera. This is the same TMT system that was used in the high efficiency transference of electric power series. We've got it separated in two labs, so the overall research lab that I have here has three buildings, two of which are joined together, and we're in one of those, and one which is separated from that. So we have the transmitter here in this building, and we have the receiver in the other building, and I will show that shortly. The system we're using for the generator is the linear amplifier generator that I used again in the high efficiency transference of electric power. I went through that generator in a lot of detail in both the video experiments and the write-ups, so I'm not going to go through that in more detail here. I'm just going to point out the key components and then utilize that in a very similar way that I did in the previous experiments. We're going to use also bird power meters. I'm using the digital ones now. They're the model 4391 bird RF power analyzer. The good thing about the digital display is it gives a much easier readout, and particularly for the video experiment, and I've got one of those at the transmitter and one of those at the receiver. So this is also the first in the series which is going to become Telluric transference of electric power. That is looking at what Tesla spent so much time trying to do throughout his research into electricity. Obviously Tesla's wireless power has received a great deal of interest, and there's a lot that you can find online with lots of different perspectives. Some people believe that that system couldn't work at all. Others go into a great deal of analysis and detail on how it was supposed to operate, how the power supply worked, how the generator works, and what is the mechanism of transmission of power using that system. I've been looking at Telluric experiments over the years. I haven't reported any video experiments up until now, so I'm going to be doing a sequence of those over the next period, which will go into more detail as to where I've got with this fascinating area. So this first video experiment is going to be two video experiments. The first is with a 30 meter single wire. Now, just to recap on this Tesla coil again, this is a cylindrical coil, very similar in design. I go into the design in detail in the high efficiency transference of electric power series. It's very similar in design to a coil used originally by Eric Dollard. He used that in his induction generator, cosmic induction generator experiments, and I've subsequently used it in more recent transference of electric power experiments. It is nominally in the 160 meter ammeter band, around about 2 megacycles, and it can be fine-tuned and adjusted in a number of ways, which I'm going to go into more detail before we start the experiment. And as I said before, we have a corresponding receiver coil of the same format here. in the other lab. So this is now connected with a single wire. So we have a single wire coming off at the bottom end. That wire goes up, over, across, out the lab, and proceeds all the way around the outside of this building and across to the other lab and in the same kind of way. There is also, this is the Telluric, for the Telluric experiment. It's a 0 AWG microstranded silicone coated ground wire that connects to the bottom end of the secondary coil, and that proceeds outside of this building, and there is a specially designed and constructed ground system outside, which I will also look at in the second video on this experimental page. So what I'm going to do is, before I go through in more detail the setup here, let's have a look where the receiver is. You can see actually I'm using the dual camera. Again, I've got a camera set up here at the transmitter, and I've got a camera set up on a receiver that's in remote mode, and that comes through the network system, and I can see the experiment up in the other lab. I'm just going to go up to the other lab now and go through what we have up there. Okay, so this is what we've got in the other lab now. This is the receiving coil. Again, it's the same, it's part of a pair, same design, same geometry, nominally almost identical coil. We have same power meter, the Bird model 4391 digital meter, and we have a 500 watt load, incandescent bulb load at the output of that. Now we can see the single wire coming through here, and again we also, over the back here, we have a ground system connection. It's the same 0 AWG wire that comes from the ground system which is outside this lab. The ground system is more substantial at the transmitter, but again I'm going to be going through that when we get to the Telluric part of the video. So connected in here at the base of the secondary, and measures 30 metres, exactly 30 metres, all the way around to where it's connected into the base of the secondary coil at the other end. We have the usual variable vacuum capacitor, KP112, adjusts from about 20 picofarads up to about 1200 picofarads. That is connected on in parallel with the primary, and the primary here we've got using maximally all four turns on the primary coil. Coupling is set optimum in the way that it was before. There's somewhere K, the magnetic coupling coefficient is around about 0.2 for this system. Now also we see at the top end here we have a telescopic aerial, and this allows us to make very small fine-tune adjustments. So essentially the fundamental resonance series mode of the secondary coil is predominantly set by the wire length, and by adjusting this telescopic aerial we are in effect adjusting the wire length at the top end, and this will also affect that series mode frequency, that fundamental series mode frequency. Then of course we've got the two parallel modes. Tesla coil has both a series mode and a parallel mode. When it's combined with the primary in itself is self-resonant, at a much higher frequency. It has its own series mode, and it also has a parallel mode. That parallel mode is usually much lower than the series mode, so it's a much bigger spacing. That's because of the imbalance between its inductive reactance and its self-capacitance, which is very low. That forms its self-resonance. But the separation between the series mode and the parallel mode is quite wide, and I go into that in a lot of detail on other posts on my website that are looking at the small signal input impedance of Tesla coils Z11 and also the transfer gain of a Tesla coil S21. So we can adjust this with the wire length, and that's important to be able to adjust very finely. We want to be able to very finely match the two together, and also and find the balance point for the parallel modes. So in other words, that gives, and both of those modes are important. Balancing and matching the series modes between the transmitter and receiver and the parallel modes is important in setting up the overall TMT system, or Tesla's magnifying transformer electrical distribution system, in effect. So we have that cavity of the single wire, so the secondary coil of the transmitter through the cavity of the single wire and the cavity of the receiver, and coupled to the primary. Then we take that out, we have the parallel capacitance that comes through the power meter and goes to the load. And when we're actually running, I will point the camera, I will zoom in the camera to this region so we can see what's happening both in terms of received power and also how much illumination we're getting on the load. These smaller bulbs are not connected. This is just a combined load that I use. These are 25 watt incandescents that I use in some experiments, but the one that's connected in this experiment is the larger 500 watt light bulb. Okay, so this is the receiver. I'm going to set up the camera now for a remote operation. We'll come back to that later when we actually run. And then first of all, we'll take some small signal AC impedance measurements from the transmitter perspective. Look at how these two are matched. At least that's using a DG8 SAQ VAWA vector network analyzer that I use on many of the posts and the website for this kind of analysis, and we will see what the transmitter can see. So the first question is can, down this very long wire, can the transmitter even see the receiver? Now it will be able to in this case because the impedance of the wire is low, even at the frequencies that we're talking about. There is this wire is a 12 AWG microstranded silicon coated, and even over 30 meters, we've got to recognize that's only still a fraction of the wavelength. The wavelength we're operating is approximately 160 meters, and we're operating in the close midfield region. So in other words, the transmitter coil and the receiver coil, they're not in the same building. They are technically in the midfield in high efficiency of transference of electric power series. In the first experiment, they was in the close midfield at 1.5 meters. In the second experiment, they were separated by 11 metre single wire. I had them in opposite ends of the other lab buildings, now separated at 30 metres. We're in the midfield region, but we are still well within a wavelength. We should also take into account that we are at 30 metres, we are only 10 metres away from a quarter wavelength. So the quarter wavelength involves a impedance transformation, and that is also significant. I do actually have a 10 metre extension that we can add to this single wire and take it into almost exactly a quarter wave transmission line. Okay, so I'm now going to go down to the other lab and we'll have a look at the small signal analysis. Okay, so I'm back down with the transmitter and I've set the camera to look at the close-up screen of the computer, which is connected to the VNWA at the back here. I can just bring it in slightly, you can just see it on the edge of the camera there, and that is connected to, let me see if I can swing the camera around a little, that is connected to the input here via the BNC of the transmitter coil. So bring it back to the screen, it's fine. I've calibrated that in a normal way, and at the moment I have just the transmitter coil, and the lower end of the secondary coil is connected down only to the RF ground. So there's only one coil involved here, we're not connected via the single wire to the receiver. And we'll take a scan. That's a typical scan for a cylindrical Tesla coil with a vacuum variable primary tuning capacitor, or it doesn't have to be a vacuum capacitor, but with a parallel tank capacitor connected across the primary and set in balanced mode. So we have down here at marker 1, down here we basically have the fundamental series resonant mode, and that is let's just move that out of the way slightly, that's 1.88 megacycles. Now this is nominally a 2 megacycle coil, so if I remove the telescopic extension at the top end of the secondary coil, it is, and connected with the bottom end down to RF ground, it is exactly 2 megacycles. With the telescopic top end, we see with the extra wire length we have a series mode of 1.88 megacycles, which keeps it nicely in the 160 meter ammeter band. We have the two parallel modes. There's the lower parallel mode here and the upper parallel mode. Let me just add a marker. So that lower one, that's 1.62 megacycles, and add another one. Oops. Drag that. And that's at 2.2 megacycles. So we have the lower parallel mode and the upper parallel mode. One of those parallel modes comes from the secondary coil, the other parallel mode comes from the primary coil, and when they are coupled together like that, there is beating, there obviously is frequency splitting, and in a sense, if those coils were pulled far apart from each other, we would find that the parallel mode of the secondary and the parallel mode from the primary would essentially be at the same frequency. So the tank capacitor in the primary circuit in parallel brings the primary parallel mode to the same frequency as the secondary. When they're coupled like this, then we get this splitting, and that forms the lower and upper parallel modes. So that is typical for a Tesla coil. There's a lot of detail, more detail about this type of Z11 small signal AC input impedance. On my website I use this kind of analysis a lot, and there are pages that are dedicated to looking at this in a lot of detail. So now we've got the typical characteristic. I've got 4 turns on the primary, so I've set this is adjustable primary. I've got it set to 4 turns, which is the maximum. So now I'm going to unplug the RF grounds and I'm going to connect it to the single wire. Okay, so I connected the bottom end to the single wire. I'm going to take that sweep again. Okay, so first of all we have another phase change. Not a great deal of difference to the 2 parallel modes. That's because I do not have the capacitor, the vacuum variable capacitor. The receiver is not currently connected. I will connect that in a minute, but I wanted to take it just a step at a time. But the main difference that we see here is at the series mode. So in other words, now we have 2 phase changes. So along that 30-meter wire we can now see the fundamental series resonant mode of the receiver, and we see obviously again with split, so there's splitting going on. So down here, if I just zoom in a little bit, okay, so we can see we now have 2 minimums. We have one at, just get that on, at around about 1.85. So go down from 1.88 to 1.85. I'll just add another frequency marker. I will put all these results onto the write-up so you can see exactly these measurements in detail. And we have the upper one at 1.93 megacycles. So we've got 2 phase changes there, 2 series modes which are coupled because of the single wire. And we can actually see that receiver at the end of this single wire, and that's going to be important when we come on to the second video for the Telluric work. But with this single wire we can see that, and I'm going to do some small adjustments now. So I'm going to make small adjustments to the length of the telescopic extension at the end, just to move around the series mode of the transmitter. So let me first of all put it right in, so it's at its shortest. So we would expect the series resonant mode of the transmitter to be at its highest. We see that's moved up. Let's go put our marker back to 4. 4, let's move this out of the way, is now 1.96 megacycles, which is what we would expect. We're starting to get close. The top telescopic extension is reduced to the minimum, so we are getting closest to the 2 megacycle, the fundamental, the 2 megacycles when we don't have a top end extension. This extension is as a result of this here, is a result of the receiver. So, and we see now as I move them apart, the transmitter is now dominant here, and a much smaller resonance as they move apart, as their fundamental frequencies move apart. So I'm going to add that back again. So I'm going to first of all add just a 10 centimeter extension on the telescopic area of the transmitter. Sweep that again. Okay, so it's coming back in again. I'm going to extend it a little bit further, another 10 centimeters. Okay, now we're very close. Now the two are very closely matched. So the series fundamental resonant frequency of the transmitter and of the receiver in this situation are almost exactly the same, based upon their telescopic extensions. If I take it a stage further, I'm going to add another 10 centimetres for the transmitter, and we just start pushing the other way. Okay, so now we start pushing the other way. So again, they have moved through each other. This lower frequency is now at, let me just put the marker in the right place, marker 1.82 megacycles. So it is basically now less than. Again, it's the transmitter. This is now the transmitter, the lower one. This is now the receiver, the upper frequency. So they've had, the frequency have passed, the resonant frequency have passed through each other. The gap between them caused by the splitting, and that is defined by the coupling that's going on down this 30-metre single wire. That 4, we'll put that back around the minimum, 1.92 megacycles, so it hasn't changed a great deal. So let me take off 10 centimetres of that. Okay, very, very close. Just going to try and get it even closer. Just take a centimetre off of the extension. No, that's too far. So just add about another centimetre. No, that's too far the other way. Very, very fine adjustments. Very high Q resonators. Closer. Just taking a millimetre or two change. Closer. Take a little bit more. There. That's very close to they resonating at exactly the same frequency. Very sharp transition from both of them means that they're both very high Q resonators at the same fundamental series resonant frequency. Just adjust that to there, it's good. Middle of the phase change, 1.85 megacycles for marker 1, 1.92 megacycles. So separated, the frequency separation here, 70 kilocycles. So this defines our two possible operating points. I haven't brought the parallel mode in yet. We see we have the two parallel modes here, and we haven't yet considered those. They're almost at balance correctly at the transmitter, but we haven't brought the receiver in yet. Let's just zoom out. We look at that overall. Let's just balance up our parallel modes a little bit. So I'm balancing it slightly. Very sensitive. Let me put it on continuous sweep. If I can do it in real time. Very sensitive coupled system. balance through it slightly. The balanced parallel modes, and equal frequency series modes. Right, what I'm going to do is I'm going to put the parallel tuning capacitor on at the receiver, and then we balance to our best of our ability everything together. Okay, so I've reconnected the parallel capacitance at the receiver. That's in the primary circuit. Taken another sweep, and we see it's made a very little impact to the balance of the overall system. Just put these markers back, and let me just take a fresh scan. Okay, put the markers at the top. Set. Just get these in the right place as well, and then we have an overall look at what we've got. Okay, getting the phase in the correct place. Alright, so when we look at that now, so we got our two series modes from the transmitter and receiver at markers 1 and 4, which is 1.85 megacycles and 1.92 megacycles. We've got the parallel modes that we can see here balanced at markers 2 and 3, and that is 1.64 megacycles and 2.28 megacycles. So our series modes and our parallel modes balanced, and the series modes and the parallel modes are both important for the highest efficiency for transference of electric power. And as I conjecture in many of my write-ups, I have found that the highest efficiency comes when the TEM modes are balanced in the primary of the transmitter and the receiver, and the LMD mode is balanced in the cavity between the transmitter and the receiver. And the parallel modes have quite a bit of impact in terms of the LMD mode. The series, it's important to get the series fundamental modes. So here markers 1 and 4 equal to each other in the transmitter and the receiver. So we are the transformation in a Tesla transformer between the primary and the secondary. The transformation, I conjecture the transformation between the TEM, transverse electromagnetic mode in the primary in the half wave coil, to the longitudinal magnetodielectric mode in the cavity formed by the secondary coil, which is then extended by the single wire to the cavity of the receiver coil. And that it's important to have those 10 modes match in the primaries for the highest efficiency of transformation of the LND mode from the 10 mode to the LND, and the LND back to the 10 mode. At the end of the day, we require the 10 mode in order to do work at the generator, supplied by the generator, and to do work at the load. And that LND mode, the optimal transmission mode between the two. And with that, I do talk about this in a lot of detail in high efficiency transference of electric power, particularly in the 11 meter wire, where we got very high efficiencies and higher than you would expect when you take into account TEM radiation, or transverse electromagnetic radiation off of the single wire. And we're also going to expect that here as well. A 30 meter single wire, we would expect that to be quite an efficient irradiator for the transverse electromagnetic mode, especially for where we're operating 160 meters at 30 meters. for the length of the wire. So we would expect, if the 10 mode is involved or dominant in the power transfer as the transmission mode between the transmitter and receiver, we would expect to lose a lot of power. If we can get the LND mode dominant, then we would expect the efficiency to be much higher, based upon the conjecture that I'm making. Let's see what we can accomplish in this experiment. We may have to do the experiment several times in order to accomplish a comparison between the TM and the LND mode. So that's, I think, everything for now on Z11, the small signal AC input impedance to the system as measured with a vector network analyzer. I will put these measurements on the write-up page, so there one can see all the points. I can see the things that I've just demonstrated here, and with better resolution. I don't know whether the very small print of the software will come out on the camera, but I will put those. I've explained what the marker points are, and I will put those results into the write-up. Right, so I've set up now. I've tried to find the best camera angle so that we can see all of the instruments and the important parts of it. I will need to lean in a bit and make adjustments, typically here and here, so that will obscure some of the instruments during the experiment, but I will try to make sure as much appears on the video as possible. So just very quickly to recap the generator, we have a Kenwood TS430S as the exciter unit. This is modified to the overall band transmit, including the intermediate, and I use it as a high power, basically up to 100 watt bench top generator. That is connected to the linear amplifier, nominally 1000 watt TL922 Kenwood. That goes through MFJ auto tuner, which also shows a digital form of SWR. It shows power, forward power and reflected power, and we will be able to see the power output that the generator is producing here. We then have a PowerStar 85K manual antenna tuner. I'll be using this to make sure that we keep the SWR, the standing wave ratio, between the generator and the experiment to a minimum, so we can get maximum forward power through. That comes out of there, it goes through the Bird 4391 through line power meter. This is set to, this has got a 1000 watt slug in the forward direction between 450 kilocycles and 2.5 megacycles, and then we've got a 100 watt in the reverse, in the reflected direction. That comes out of there and it goes into a PowerStar 4 kilowatt balun. We are essentially going from unbalanced coaxial feed from the system to a balanced output to a half wavelength primary coil. So we use the balun there to convert from that unbalanced to balanced output. That's a very low insertion loss current balun, 1:1, and then we will be doing the matching directly from using the manual antenna tuner. So that's the system. At the other end, of course, then we go down the single wire for over the 30 meters, and at the receiver we can see here that is actually in the other lab, and we've got the power meter there and the load. I've already shown the setup there, and I will put that in the screen as an overlay on this video, so we can see what's coming at the other end as well. So going back to our AC signal analysis, the best driving point, because we are driving with a linear amplifier here, we're going to drive directly at the series fundamental resonant mode. We had two of them split because of the two coupled resonators. The The lower one was at 1.85 megacycles, and the upper was at, those were at markers 1 and 4, is at 1.92 megacycles. So I've set the exciter here at 1.92 megacycles. We'll use the upper series mode. Everything's off. So first of all we have to do some tuning and matching just to minimise our SWR. So I'm going to make sure I'm wound down fully. I'm going to turn on to transmit. I've got the linear amplifier off at the moment. I want to just run with the power output from the transceiver. I'm going to wind up a little bit until we get some power going through. Okay, good. So it's about 21 watts here. Let's adjust. The SWR is already about 1.3, which is quite good. Let me just see if we can improve that. Oh, let me just first of all coax 1 tuned. Yep, that's fine. Okay. Okay. So we're already at a pretty good point. I'll just see if I can make any improvements there. Very sensitive. The Power Start antenna tuner is a T network. Okay, so 1.2 seems to be about the best. We'll make more adjustments to that when we put the power up. So we can see now the Bird 4391 here at the transmitter and at the receiver at the other end here. We can see we've got some power coming through there. They are calibrated together, so calibrated in line, so at a level of 500 watts. So they are accurate with each other. They're currently showing 29 watts at the transmitter and 11 watts at the receiver. 30 and 11. So about, at this very low level, about a third of the power that we're putting in at low level is arriving there at the receiver. We see the power output from the generator measured here is slightly lower, it's slightly different. This depends very much on the setup of the antenna tuner, what the final result will actually be. Ultimately, if we can get the system matched very, very well, then we will end up with everything this reading almost exactly the same as this. With a slight reactive component, capacitive or inductive either side, then we're going to get some difference there. And we're going to try to minimise that, but also the actual measurement I'm going to use for the transfer efficiency is the final power going in to the primary circuit through the balun and the circuit and the power coming out of the receiver at the other end. Also, when I look even at this low power, I look at the top end of the Tesla coil. I'm not sure whether one can see it on the camera. There's a neon bulb connected at the end where the wire extension is, and that's now illuminated even at this low power. Okay, so I'm going to go up in power. SWR stays nice and low. We can see, so I've got 119 here, I've got 44 at the other end, and we can see that the 500 watt bulb is very slightly illuminated. Okay, let me wind back down, and I'm going to switch over the linear amplifier so we can actually put some more power. That was a maximum output that this exciter could produce by itself. Okay, so I've started both of the cameras at both ends now, so we can just do a short run again. Again, we're back at 1.92 megacycles. Linear amplifier is operating. Let's just bring the power up slowly. So it's 155 watts there, 129 there, 56. So running at about a third. Let's bring it up to 100 at the receiver. Minimise 90 to 79. (201 to 622). Breakout at the top, 259, 833. That back to about 200 isn't easy to read. About 198, 633. 207. Now let's detune slightly. Let's look at that. 278 to 919. So reactive components make a very big impact on the measurement. The optimum point really does seem there with the SWR. Around about there, 196.19, 210, 675. Let's just check the linear amplifier setup. Also looks pretty good. Much more. Try making a broader change of the linear amplifier settings, see if that affects our efficiency. So our optimum power throughput comes around about there. Again, it's just around a third. (212, 700). Again, it's still about the same. Keep that around about 200. Received at the other end. And 62, 530. Still just around a third. 180, slightly detuned. Let's just adjust in frequency. Optimize. Forward does seem better, very big mismatch here, 133, that doesn't seem an improvement. Just keep it, sweep around a little bit, not going too far away. To find our optimum point. The maximum power seems to be getting through there, but for quite a lot of input. That still seems to be our whole system. That's 300 watts, 1000 going in. And your amplifier at maximum, still around a third. So 100, we'll do a little parallel mode adjustment. See if we can make an improvements to the efficiency. Getting worse. We've got that out. .87 at the end. It really is about optimum. There, 101, 330 in, 1/3. So 200. Detune slightly, flare at the top. $650 to $193. $300 to $1,000. Just less than a third. So that seems to be, again, I wanted to record what was happening at the receiver. Early on I didn't start the video, so 250, half illumination. Of the load at the other end. 500 watt load, 245 watts being put in. Small flare at the top end of the Tesla coil at the sharp point that I use there with the neon light. 640 here, 844 here. Efficiency is a bit less than a third. Nice and stable. Good. Okay. So we weren't, in conclusion, so far we've not been able to get the efficiency of this single wire experiment at 30 meters between the two coils, up much above a third. Different tuning points. We tried both of the series resonant mode to the two coupling around about 1.85 megacycles and about 1.92 megacycles. 1.92 megacycles seems to be easier to adjust the right efficiency. At 1.85 megacycles we were to get good, we could more easily cancel out reactive components between the generator and the transmitter, so we had good correspondence with the power coming out of the generator and the power going into the secondary coil, and that has to do with what's reflected. So I'll just demonstrate that actually, that if I now wind up again up to 100 watts, I'll show what I mean by the reactive. So 100 watts there, we've got 260 going in, got 306 here. If I look at what's reflected, it's telling me that 74 watts is being reflected I've got 308. So if I take the 308, 74 for 304, it takes me down to about 330. Sorry, 230. This is 260. So we need to check the reflected power, which is not indicative of the SWR that's being read there. Complicated when you have reactive components involved. So one-third is about the best that we could achieve here. I would say that that means that we are not tuning the LND mode in between the two. Also, the fact that we are closer to quarter wavelength may also have an impact, and we'll experiment further with that on subsequent experiments. But this is to set the basis. I believe that the 10 mode was being used in transmission between the transmitter and the receiver, and that energy loss is primarily lost through radiation between the transmitter, radiation off the wire between the transmitter and the receiver coil in the other lab. Okay, so I've just been making some adjustments, trying out some different configurations, different number of turns on the primary, both at the transmitter and the receiver, just to see whether I can increase that efficiency anymore. And it does turn out that the optimum position seems to be with 4 turns of the primary of the transmitter, 4 turns of the primary on the secondary, and with the primary tuning capacitors balanced. So what we could see from the Z11, the input impedance, was quite accurate in terms of the optimum balanced mode. Now, what I did try afterwards is just removing the balun. I had a balun here to go from unbalanced to balanced connection to the half wavelength of the primary coil. So I took that out. I'm not using it anyway at the receiver end, so I took it out from the transmitter and just connected by an ordinary piece of coax from the output here to the end. And what we find is that does give a bit of an increase in efficiency. I'll just turn on. Let me just start the camera at the other end so we can show what's happening there as well. Now if I wind up, I bring up to about 100 watts. I also find that the correspondence between the power here and the power presented here is also much closer without the balun in. So there is obviously in this section less reflected power. The reactive components are better balanced out without the balun in place. So this is reading just on 100, this is reading 102, and we've got 38 on the other side. So almost up to 40%. Frequency I've also adjusted down from the upper serial point, which we were running at 1.92 megacycles, much closer down towards the lower serial points at 1.85 megacycles. Now, interestingly enough, the 1.89 is very close to the actual resonant frequency, free resonant frequency, just ground connected when they are not connected by the 30-meter single wire. So there's very good correspondence now. 112, 113, just look at the reflected power, very low. So there's good correspondence. Notice that the SWR is up at 2.1. I'm going to, and I've also found that that helps with efficiency, not to have it directly as 1. Probably produces a better match actually at the interface between the primary coil and the antenna tuner. Yeah, that actually leads to a worse scenario. If I wind that back up at about 1.92, seems to be about the optimum position. Let's put it on 2 for the moment. I'm going to increase power at the load. Let's go up to 200 watts at the load. 203, here with 509, so just on 40% efficiency. So far that's the best efficiency that I've gotten out of this experimental apparatus at this time. Really does seem best. That's over. We match the power here to the power here, which I believe is the best reactive match to the coil. 514, 513, 514, 200, 199 coming out. We can drive more power as well. This also seems to be the best point to drive maximum power. 263. Let's see if I can adjust that up a little bit. Just the linear amplifier. 300. Careful adjustments at this high driving power. 30. Let's just back off to 200 for a moment. Just check that our efficiency hasn't gone down as a result of that. So 200 exactly, 524, so about the same efficiency level, but we can push 325 power at the receiver, 845 in, 820 there, 847 there. That's about, the linear amplifiers are just off its maximum. SWR of about 1.6, we could probably detune that slightly more. Be careful with these high powers. 1.8, there's 811, 811, and 309 at the other end, so slightly lower. Really does seem it's about there, 1.5. 322, 853. Down to 200, slightly better on the picture, the bulb's not so bright. 202, 540, down to 100 watts received power. 288 at 101, efficiency falling off slightly. 50, 49 watts, 136. Back up again, 200, 210, 204, 547, 522 here. Okay, so 40% efficiency. Again, I think it's still similar conclusion. I think we're not really establishing the LMD mode, if that's possible to establish over this distance. We're not really establishing it. I think we're losing most of our power with radiated losses from the single wire between the two. The effect also of quarter wavelength. I'm going to add a 10 meter section at the other end to bring it almost to exactly quarter wavelength, and then we see if that efficiency is worse or better. I would expect the efficiency to be worse as we approach quarter wavelength. Okay, I've added a 10-metre section at the other end, at the receiver end, so now the single wire is 40 metres long. And at the frequency that we are operating here, 1.89, let's assume that the propagation in free space, C, then at 1.89 megacycles we have a wavelength of 158.6 meters. So we are approximately at the quarter wavelength point. So the receiver is a quarter wavelength away from the transmitter at the bottom ends of the coils. Remember, we've also got to consider the wire length of the coils themselves. So in actual fact, the wire length of the secondary, the single wire transmission medium and the receiver secondary is considerably longer, but the single wire in between is almost exactly quarter wavelength. So let's see if that has any impact on our results. Turn on again. Let's just check what our match is first of all. Rewind up a bit. That's not too bad, the standing wave ratio. I'm going to bring it down to about 2, or let me maximise at the receiver. I'll start off with about 2. 164 there, 170 here, 65 at the receiver. Let's bring it up to 100. 108, 278. Still very much the same. Let's bring it up to 200. About 200, 199, 501, 485 here. So very comparable. No, just optimise. Let's find the optimum point. Looking at the receiver power at 235. $5, 600 watts in, 622. $203, it's 520. Again, very comparable, very close to the 40% mark. Let me just see what that is precisely. So 208 divided by 537, 38.7% efficiency. And an SWR. Let's see if I can improve just slightly. That seems to be about optimum. 201, 521 here, and 531 output there. So close correspondence between these two. So there's a good match through the system, out of the generator, through the antenna tuner, through the meter here, which is better also now without the balun, a slight improvement without the balun, and then directly to here. Reasonably good correspondence, and then there's 199 watts received at the other end, down a 40 meter single wire now. So it's a 30 meter with a 40 meter with a 10 meter wire extension, quarter wavelength. Good. Okay. A variation with a slight increase in efficiency. Primary tuning, the primary tuning capacitors remain exactly the same. I haven't changed that. So the optimum place that we set it up with the vector network analyzer, that appears to be the at least in this experiment, the optimum place where we could get the maximum power from transmitter to receiver. But I still believe that we are doing that in the TEM mode, and we are still not for some reason that we've yet to discover, engaging the LND mode in this apparatus in the way that we did in the high efficiency transference of electric power over 11 meters, where we were able to go over 95% efficient. There I think we were able to engage the LND or tune the LND mode. Good. Okay.